All right, goal of this tutorial is to define two key parameters associated with fluids, density and pressure. We'll define them, give some units, examples, and one problem, and we should be good to go. From there, then we will develop concepts of buoyancy, fluid pressure, and eventually fluid flow. So this is critical, foundational stuff, pretty straightforward. We'll have practice with it in class. All right, so fluid, we talked about in class, is anything that flows, okay? In other words, a liquid or gas. It doesn't have any definite shape. There's an important distinction between a liquid and a gas, we'll talk about in a second. But fluids, the important properties that are generally associated with fluids and that we want to define, as I mentioned, are density, which is given a symbol rho, pressure, volume, and temperature. Temperature is not going to play so much role in this chapter. It will come in when we talk about gases and gas laws. So those are all, except for volume, really new measurements in our understanding of nature, at least through physics. Distinction between liquids and gases, all right? Gases are compressible. In other words, their volume isn't necessarily constant. You can simply change the volume by putting pressure on it. Liquids, you generally cannot. You have a bottle full of water, take a pop bottle, a glass pop bottle, or even a plastic 2-liter bottle, fill it to the brim with water, and you try to push down on it, you cannot shrink it. You cannot make it take up less space. And so that makes gases a little bit more difficult when you're talking about density. In other words, the density of a gas depends on its pressure or depth, which can be altered, even temperature for that matter. Whereas in a fluid or a liquid, generally the density depends on the fluid itself. Okay, so let's define density. It is a property of a material, okay? And it gives a ratio of mass to volume. So density, of course, is mass over volume. In this chapter, we're not so much interested in calculating the density of a material, but rather, given the density, use it to find mass, okay? So it's going to be a proxy, an alternative way of looking at mass that's going to show up in a lot of equations. So it's really good to know off the top of your head that the mass of a material, okay, is equal to its density times the relevant volume. And that's going to be, the volume part can be the tricky part for a number of these problems. But we'll hit upon that another time. Okay, so let's do density of water in SI units, okay, metric units. You know from chemistry that the density of water is 1 gram per cubic centimeter, okay? The standard units used in chemistry are grams per cubic centimeter. In physics, we can use that in certain applications, but in other applications where we're mixing in other metric units, we need to have it in kilograms per cubic meter. So you should be able to do that transformation. So I'm going to do it the old-fashioned way, stoichiometry. We have 1 gram per cubic centimeter. So I'm going to take care of the mass part. So I want kilograms on top. So we have 1 kilogram is equivalent to 1,000 grams. So my grams cancel out. I need per cubic meter. So I want meters cubed on the bottom. So how many cubic centimeters are in a cubic meter? If you're careful, you won't say 100. It's 100 cubed. Or 10 to the 6th. Did I do that right? 100 cubed is 10 to the 6th cubic centimeters. So our cubic centimeters cancel out. So we have 10 to the 6th on top divided by 10 to the 3rd, which gives us 10 to the 3rd kilograms per cubic meter. All right, that's pretty dense. It's 1,000 kilograms, a metric ton, if you have a box that's a meter wide, meter tall, and a meter deep. All right, so water doesn't seem heavy or dense, but it is fairly dense. All right, another calculation we should be able to do off the top of our head is given a density, find a mass. So let's take the air that fills up this room, the classroom that is. All right, it is known that at least at our altitude, sea level, the density of air is fairly low. Note that it's 1.29, which might sound, wow, heavier than water, but it's not because this is kilograms per cubic meter, so it's, 600-700 times less dense than water. So to find the mass of the room, we want to find a volume. So let's estimate it. We're treating the room as a cube. So let's say that the length is 10 meters, the width is 10 meters, and let's say the height is 2 meters. Keep it simple. And so that gives us, of course, 200 cubic meters. And so the mass of the room would be the density, 1.29 times 200 cubic centimeters. Excuse me, this should be, I won't put the units there, because I don't have space for that. And work out the math, and we have 258 kilograms. That's a pretty decent amount of air pushing on you. All right, 258 kilograms multiplied by G gives us about 2,500 newtons overall, but it's spread out. And so it's not so much talk about the weight of the air in a room as opposed to another measurement, of course, which will be pressure. But before we get to pressure, let's look at one other aspect, a new vocabulary term that I'm hoping you're familiar with, but if it's new, pay attention to it because it does come up, and that's called specific gravity, SG. Specific gravity is an indirect measure of density. It's based on the density of water. So the equation, if you will, for specific gravity is the density of the material in question divided by the density of water, because water is really a baseline for the definition of a cubic centimeter, or a gram is equal to 1 cubic centimeter when you're dealing with water. So it has a lot of historical significance. So for example, if we know the density of lead is 11,300, we know that lead is more dense than water, and we ask what's the specific gravity of lead? Well, that's pretty simple. Basic definition is 11,300 units divided by the density of water, which is 1,000 units, or 11.3. So it has no units, it's a ratio. So that's a nice way of saying, rather than giving the kilograms or cubic meter or whatever. And it doesn't matter what units you choose, the specific gravity 11.3 can be applied to any density units. All right, the second important measure associated with fluids is pressure, okay, capital P. Pressure is related to force, whereas density is related to mass. We're going to use pressure as a proxy for force. The definition is fairly straightforward. It's force per unit area, okay? So it's how spread out the force is. The equation is very simple. Pressure P is equal to F divided by A. A can be pi r squared if it's a cylindrical cross-section, or excuse me, a circular cross-section, length times width if it's a square cross-section, or any variation thereof. Sorry, pressure is, even though it's a force divided by area, it is a scalar quantity. You do not generally talk about direction with pressure in the sense of north, south, east, or west. It's a little bit of a gray area, and sometimes we'll say it's pushing up on something or pushing down. And while that's true, it's not considered a true vector. Units come from force divided by area, so that would be a Newton per square meter. I almost want to say Newton per meter. That would be the spring constant, but units of area, square meter, and that is called a Pascal, after Blaise Pascal, French physicist, chemist, who did important work in the 18th century, I believe. All right, so we're going to hear of Pascals a lot. There are many, many units with pressure, depending on what subject you're looking at, meteorology, oceanography, etc. And one of the key things you want to know is atmospheric pressure, which I'm going to call P atmosphere. Actually, sometimes I might call it P naught because it's so common and we have to take it into account. It's good to know, not that you have to memorize it. I believe the key value is in the reference tables, what air pressure is, standard pressure at sea level. All right, so you may have heard this number before, I'm not sure. Notice this is in kilopascal, so 1,000 pascals, it's 101. Usually we just say 100, but I'm going to put 101. So just being at sea level, you have 101,000 newtons of force pushing down on per area, unit of area. Right, so if your head, let's think of that, right? Let's treat it as a square, as let's say 10 centimeters by 10 centimeters, that's 0.01 square meters. Multiply that by 101,000, and you got about 1,000 newtons, or is it 10? Yeah, 1,000 newtons of air pushing down on you, or pressure on you. PSI is pounds per square inch. You often see that when inflating tires or a basketball. So atmospheric pressure is 14.7. Not that you have to memorize that, but that's a convenient thing to know. In terms of atmospheres, it's essentially 1 atmosphere. That's a convenient way of expressing it. And you may remember from chemistry, millimeters of mercury. That's an old way of looking at it, but it's still in use, and that's 760 millimeters of mercury. There are sometimes you hear bars as well, especially with weather. And then there's, I forgot how many bars is an atmosphere. I don't know if it's 100,000 bars, or it basically transforms the 101,000 into 100. It's just an easier number to look at. When we measure pressure, and I'll talk to you more about in class, you have pressure gauges, right? They can be digital, they can be analog. If you ever had an air compressor, the pressure gauge is a very important measure to see if you're overinflating your tire or your ball. Measures measures a certain type of pressure that we often don't distinguish. Okay, so we want to distinguish between two types of pressure that are very much related, but you have to be careful of which one you're using and depending on the equation. So what am I talking about? Well, there's something called absolute pressure as opposed to gauge pressure. All right, gauge pressure, you can kind of guess, is measured by a gauge. So what distinguishes it from absolute pressure? All right, absolute pressure is due to all forces. And that really is a way of saying that it's, or especially from the atmosphere. Okay. Now, with this implicit in what I'm saying here is that when we measure pressure, gauge pressure, it's a pressure above and beyond atmospheric pressure. So if I'm inflating a basketball to, well, let's say my bike tire, because that's what I know off the top of my head, is let's say 50 psi. That's a gauge pressure. The absolute pressure in the tire is 50 psi plus atmospheric pressure 14.7. And you might ask, well, why don't we just include that in there? Why do we distinguish between it? Well, that's because air pressure, and we'll talk more about this with some demos, is on the inside and the outside. So generally the air pressure, the net pressure due to the atmosphere cancels out. And so what matters is the above and beyond part, the gauge pressure. So that's what's going to dictate how an object's going to behave, unless you set up a system where you seal off air in one arena so that the absolute pressure is the difference between inside and outside is the absolute pressure plus the gauge pressure. So the simple equation that goes along with that is absolute pressure is equal to gauge pressure, okay, plus atmospheric. And we'll make sure we're clear on when you use one, when you use the other. All right, so let's finish up with a simple